I'm going to cover engineering elements in doing high-scale broking. So I'll start by setting context about the domain, what we do. I'm going to talk about only 3 design patterns that we employ and 3 choices that we have made in our tech stack. So this is our app. It's one place for all your financial needs. So we sell stocks, mutual funds, loans. Key things to note is there are a lot of prices here. They change multiple times in a second. And when people make decisions, they look at tickers, different tickers, and make decisions. So it's very important to get the prices which are fresh right onto the apps. People also find signals from other places like near real-time insights that we bring out, like what are the stocks which are being bought most right now. We have about 22 million client bases, customer clients. We are second in terms of the number of active clients on NSE, the largest exchange in India. In terms of scale, we onboard 1 million customers every month. We touch about 10 million orders in a day, and our traffic at 9:14 is 0, and 9:15 is 3 million requests per second. So it's a pretty steep ramp. So today I'm just going to focus on equities trading and what goes in building such a system. In terms of the mechanics, this is a timeline of prices of stock X. This is a platform where people can buy and sell the same stock at various prices. And a match happens when a buy and sell order are in close proximity, both in time and price. Right? You want to buy something, and the highest price that you want to buy it is more than the lowest price that someone is willing to sell something at. So we enable the marketplace. So what goes in here? First thing, prices need to be piped real fast to the app. Once someone places an order, those orders need to go and stand in the queue as soon as possible. Right? Fast wins. Once someone does an order, then there's a lot of accounting that happens in terms of shares and funds, which then needs to be reflected onto the customer. This includes things like risk management. And finally, the order status changes, because whether your order gets filled or not depends on other people in the queue. So whatever happens, we need to pipe the information back to the customers very quickly. And all this needs to work in the face of patchy networks, server failures, or earthquakes, right? And since we are a regulated entity, we actually do DR drills quarterly. That means someone from the regulators comes to our office, starts removing wires, shutting down things, and still sees that things work. So just to emphasize, right, there are 3 ways to make money in equities trading. If you have seen the movie Margin Call, you know. If you haven't, you should go see it. Be smart, be fast, or cheat. So we don't allow customers to cheat. So the way to people make money is they are smart and they are fast. And the platform that we do basically pipes actionable insights to the customers very fast. And whatever actions they want to do, we execute them in a real-time fashion. And the patterns that we employ, the engineering that we do is all in the service of this. So this is a short demo of what we're talking about. This is a trader. He's going to look at Reliance, the price charts, and this is something called as an option chain, which has various contracts of Reliance, various dates, various prices. And then he's going to start placing orders. Right, and this is someone who's actually doing this. So you can see how fast is placing orders. Right, there is muscle memory in what they look at, various prices that they look at, and they want to grab opportunities that they see real time. Once you click orders, you also want to see what's your PNL, which is again reflected real time. All this is happening by us. The app talking to our backends. Our backends talking to the exchange, WebSockets piping back information back in, and everything happening nicely on a rosy day. So 3 design patterns. The first is eggs and basket. The basic problem we're trying to solve here is how do we ensure systems are available if there's a fire in the data center? Any guesses? Yeah, easy word is shard. So we group services together in shards. So obviously we don't have 3 services, but we group services in shards. Shards are replicated across data centers. The replication is async because we respect cap and we want to optimize for availability. Right. The replication is bounded. So what that means is at any given time, we know what is the in-flight data. And this amount of this information is used to reconcile if there's a failover. So you never lose your orders, but this information helps us that, if there is a 2-second lag or a 3-second lag, helps us to go and replay things that we have in our logs. Users are mapped to shards, right? So there's no router here. Every user's app directly talks to the data center. This is an informed decision to avoid single points of failure again. This magic happens via DNS. So, few users get mapped to certain shards, and this is a daily exercise. So we figure out or we predict hotspots, and then we try to load balance it across shards. This is more commonly called cell-based architecture, and it's come up on the tech radar recently as well. So the advantages is obviously higher scalability. We have million customers coming in every month. So we just throw hardware at the problem, and you buy more hardware, you scale horizontally. You have a reduced blast radius. So that means if things go wrong, not everything is not all customers are affected. Right, so you can do DRs in a very contained fashion. So rather than moving 25 million customers from one data center to another, we just move the shard from one data center to another, so we can contain the blast radius, and it helps with better deployments. So that means you can do canary deployments. If you have a new feature, you don't need to expose it to the whole bunch of your audience. This works well with apps. If you release an app to the app store, you can dial up and dial down how many people see the new features. With backends, it's slightly more difficult because our feature needs to work with a lot of different external systems. So having shards help us do canary deployments, blue green, and stuff like that. The second pattern which I want to talk about, I'm calling it always on. And this is on the front. The objective here is to optimize, is to give a delightful experience on the app, even when you are driving to a tunnel, right? So we saw people making split-second decisions and buying and selling stuff. What happens if you're driving through a tunnel and you want to manage connectivity? The key insight here is your phone has storage and has compute, right, which we leverage. So most processing happens on the app using local storage, and then there is basically sync between the front end and the back end. This entails complexity in both. So we'll look at the front end and then look at the back end. On the front end side, we use something called as MVVM, which is pretty common. We use room for our persistent storage. All our models are in DAOs, which lie in the SQLite database, and all the upper layers use those for showing views and for enabling the views that you actually see. Now the intelligence lies in the repositories. So once you ask for some data, each class can make informed decision whether I should show locally stored data or not. Right, and these decisions can be intelligent. For example, if market closes at 3:30 and your positions won't change, then we can show positions from the local storage without even making an API call. We know that prices change multiple times in a second, so there's no point storing them or showing prices, right? So we can make informed product decisions, whether to show a blank screen, whether to show last known data, whether to refresh behind the cache serving, right? This we can make on a per domain decision using this app. And Room is really cool in enabling us to do this. So once you do this, I mean, there is some complexity at the backend as well. And most often you'll end up having things like this background workers which try to process your request. Let's say order placement. Typically, your API calls will return a 201 saying, okay, done. And you'll pass it on to something like Kafka, right? The problems to solve in this architecture, for example, things like idempotency. What happens if your app retries? Right? It need not be you, the customer retrying. It could be an API retry on the front end. How do you ensure that we don't do $2 million orders instead of a single $1 million order that a customer has done, right? So we need trace IDs to be passed right from the app generation onto the exchange, the queue that we saw for the idempotency to work, right? So that is tricky. Then making progress in a queue is tricky, right? You're processing messages in a topic partition. You come to a message where you're stuck. An external service which you want is no longer there. What do you do? So we have a boilerplate for all our consumer code with dead letters and retry queues. And the third and last pattern that we have is external distrust, is healthy distrust, especially of external dependencies, right? So we are a marketplace, right? We take your orders and give them to the exchange. So let's say this is your dependency X, not necessarily the exchange. And there is certain SLA that the external service provides you, right? In this case, it says 99% of the time, I'm going to return in 200 millisecond. And you know what your TPS is. Right? How do you ensure this request meet their SLA even if this thing goes down? Right? So basic idea is you have a per dependency thread pool. Thread is in quotes. I'll explain later. So that if this dependency goes down, the clogging is isolated, and if there are user requests which don't need this, they are not affected at all. Two problems to solve. How do you size the thread pool? You do the maths. So you basically you start with the dependency, you figure out how many retries you want. 200 milliseconds, if you do one retry, one user request is going to take max 400 milliseconds. Next, you look at your TPS. So you are going to promise 30 requests per second. So if you have 30 requests per second, each is going to take 400 milliseconds. The thread pool size is 12, and you add some nice buffer and make it 15, right? Most people, when they use thread pools, the basic mistake they use is they use defaults, or they put insane numbers like 500, which actually defeat the whole purpose of having a thread pool. Right. So to key summary in the this pattern is do the math and don't make it fat. Don't make the thread pool fat. So my last section is on choices, starting with what languages we code in. We use Go for most of our backend languages. 3 reasons: simplicity, the runtime predictability that we have, and efficiency in concurrency. So a simple example of efficiency. So a Go stack is 2 KB, right? And most other languages, if you use threads, the stack is mapped to the OS level stack, which in Linux is 8 MB. So in 4 gig RAM, you can host 2 million Go routines and only 500 threads, right? So 2 million Go routines and only 500 threads. This allows you to be pretty creative with your concurrent programming without worrying about whether I'm going to run out of threads, file descriptors, and whatnot. So coding concurrent stuff is pretty fun in Go. If you have a function and you want to do it async, just put Go in front. And if you want to make sure that you get results from whatever is happening in the background, the constructs like select and timeouts really help you build it very cleanly. And as I said, it's fun coding in Go. For the rest of the stuff, we use Python for all our batch processing pipelines, and also stuff where we need a lot of ecosystem help. For example, we do a lot of rolling averages and matrix multiplications where NumPy and Pandas is really helpful. On the database side, going fast, on the database side, we really like plain old SQL transactional database. The ACID semantics make programming simple. Modern SQL engines are actually very extensible, and they have really good features like columnar indices. So if you have like analytical group bys and stuff like that, you should really look at what your SQL engine offers before you start using a different database for it. We cache where we really need single digit millisecond stuff, and we use Redshift for a lot of the analytical use cases that we have. As I said, the go-to is always a SQL database, and engineers need to answer why they can't use it before they start leveraging other things. The last slide, cross-platform. This is a common question which I also get asked a lot: is how do we make sure that we build UI elements in a cross-platform way? So we tried Flutter and few other things which didn't work out. What really worked out for us is plain old WebView with something called as Svelte. The reason we like Svelte is because of server-side rendering. So if you have like an involved page, then you can render the most of the page at the server side and ship it. So the first time to load of the page is really fast, and then the JavaScript can also obviously work on the client side to give you the animations and stuff like that. So this is our test on our native front ends. We use native code where we need performance, and wherever we feel we can leverage cross-platform stuff, we use Svelte. So that's it. I'm at boot number 8 if you have any follow-up questions.